groups, many fundamental groups of 3 manifolds, and much more. And still, it's a property that implies strong consequences at the level of the group, and Dennis will probably talk about that. So maybe just one example of an asymmetrical action on some hyperbolic space. So if you look at the mapping class group of a hyperbolic surface acting on its curve complex, so the G is enough, I guess. So the curve complex is hyperbolic by Mazur and Minsky, and the action is asymmetrical, and that's due to the Bowditch. But actually, it's actually rare to encounter natural actions of a group on a hyperbolic space which are asymmetrical. We'll see another example in the talk concerning the Hickman groups. But most groups that you will encounter do not necessarily act on some hyperbolic space. For instance, rags are going to act on some cat-zero cube complexes containing many flats in general. And even if the space were to be hyperbolic, generally the action is not as strong as to be acylindrical. So there's a very nice criterion due to Kazbina, Bromberg, and Fujiwara. So suppose, as usual, that you've got an action of a group on a geodesic metric space, and an element G such that. So we're just going to ask some hyperbolicity and some good dynamics in one direction. So the first thing is you want G to be strongly contracting. It has quasi-isometrically embedded orbits. And the orbits are strongly contracting, meaning there exists, well, for every x, there exists an x and there exists a constant c, such that, so if you look at the G orbit of x, if you take any ball which is disjoint from that G orbit x, you want the closest point projection on that orbit to have diameter at most c. So for every ball disjoint from that orbit, the diameter of the closest point projection of B on that orbit is bounded above by C. So if you have that condition and the second one, you want G to satisfy the WPD condition for which the probability is continuous, which is some sort of acylindricity along the orbits of your element. For every x, there exists in M such that the core stabilizer, for every x there exists an M such that the core stabilizer at R of x, and so not just any other point y, but a G translate, so Gm of x, so that core stabilizer is finite. Okay, so it's some sort of asymmetricity along the orbits of G. So if you have those two conditions, strongly contracting and the WPD condition, then G is either virtually cyclic or acylindrically hyperbolic. So that's a very useful criterion that's been used for many classes of groups, and rather than many more. But the problem is, I'm going to keep that picture for a moment, that's both the eccentricity of an action and checking the WPD condition are conditions which are extremely cumbersome to check if the space we're acting upon is non-locally compact. Indeed, generally the way you try to prove, for instance, the eccentricity of the action is to understand the set of geodesics between not only x and y, but between the r ball around x and the r ball around y. But since you're in a non-locally compact space, those two balls are going to be non-compact, and out of those non-compact balls, you have to understand those geometrics so as to get some sort of finite condition, which is something not obvious at all. And in particular, much harder than just to check the condition at r equals 0. For r equals 0, we're just looking at stabilizer of x and y, and you're asking that the intersection of those stabilizer is finite, which is something which is generally much more convenient to check. For instance, in the case of the action of the mapping class group on the curve complex. So if you have two vertices in the curve complex at distance that is 3, the associated curves fill the surface, so they cut the surface along the open disk, so the intersection of those associated stabilizer is finite. And you need a bit more to get the uniform down, but at least you see that it's more tractable. But to get the overall eccentricity of the action required the introduction of the tight geodesics by Brian, and really understanding the combinatorics of this set of geodesics. So as often in geometry group theory, there's one case which is much easier to deal with. It's the case of actions on trees. And so I'm going to explain why it's much easier. And the point of the talk is to give other criteria for eccentrical atomicity of groups, which are much easier to check. So actually the talk would have been called, I guess, eccentrical atomicity without tears. So in the case of trees, actions on trees, so it's actually sufficient to check the condition the condition at r equals 0 for trees. So the eccentricity is equivalent to just checking the condition at r equals 0, and analogously the WPD condition for is equivalent to the WPD condition r equals 0 for a strongly contracting G. Why is that? The proof is very simple. It's because the geodesics in the surface space are very constrained. So remember two balls are balls here. So if your R balls are sufficiently far apart, then any geodesic from here to here is going to have to it's going to have a lot in common with the geodesic from X to Y. So it's going to be something like this. So in particular, if I'm far enough, I can look at, say, a subsegment of length L0, the constant in that case. So what's going to happen if I take an element to the cross stabilizer of xy, and I look at what happens to HL0? So it's going to be moved by at most r. Okay, so if the balls are sufficiently far apart, it's still going to be on that portion of the geodesic. So we've got a map from the core stabilizer to let's call that names. So gamma, and the basic segment is going to be called gamma prime. The lengths are not determined yet. So some subset which is associated to H, the image of, so that's H gamma. So whenever you get two elements of the core stabilizer H and H prime that take gamma to the same element, then by the asymmetry condition at r equals 0, you get at most n0 such elements. So the fibers of that map are finite, and here you get also something finite, so you get like that. Everything that you wanted. You just need to be sure that you were sufficiently far apart at the beginning, but something like 6r plus L0 should be enough. And right, you've got 2r plus 1. Yeah. I think that works. And in case the constants are not exactly right, just do the Dells-Ambrosov trick and add 10 to the power 10 delta and r. Okay, so that's roughly the idea. And why does everything work in that case? It's because the geodesics between this ball and this ball are extremely constrained and really have to share a lot. But if you have an action on a higher dimensional space, such a phenomenon is not going to happen in general. Your geodesic might go close to, and in the hyperbolic case, it's going to be very close to, but not necessarily coincide with that segment. And since you're not locally compact, you've got no chance of using some sort of compactness argument to say something has to be finite. But still, there's a natural question. Apart from actions on trees, are there other classes of spaces for which the eccentricity of the action or the WPD condition would be equivalent to those weak forms at r equals 0? Is the eccentricity equivalent to that weak form of eccentricity and the WPD condition equivalent to WPD r equals 0? And for a strongly conducting element. For other types of spaces. The answer is yes. So for instance, it's going to be the case for, so if X is a hyperbolic capital square complex, so it's something that I use to study a few properties of some Higgs groups. Also for hyperbolic small constellation complexes, so C prime 106 C4 complexes. That's ongoing work with Anthony as well on the geometry of certain graph products. And also Anthony has a proof for actually hyperbolic finite dimensional category 2 complexes. So here the proof is quite different. Really use the combinatorics of the hyperplanes in a category 2 complex, but I'm going to focus on the strategy to attack the two first cases. And how do you use the rich combinatorial geometry of those complexes to kind of tame the non-local compactness of the space and get those equivalences? So what would be the ideal situation? So the ideal situation would be something like that. We want the following. So I'm just going to focus on asymmetricity. That's going to be the same for the WPD condition. So I've got my two balls, very far apart. So I choose the geodesics between x and y, and I would like something a bit similar to what happened in the case of a tree. I would like to, if I restrict to a sufficiently long subsegment here, I would like to control what happens for the geodesics from a point here to a point here. So I'm not going to be able to say that it has to coincide with gamma here. It has to, but it's going to, because we're in hyperbolic space, it's going to travel in, say, the delta cube, if I'm sufficiently far apart from my two arballs. And what I would like is a finite set. If that were to be the case, then the same type of reasoning would work as what we did in the case of trees, and you include again the equivalence between eccentricity and the weak form as before. So that actually, for instance, that happens in the case of the action on the curve complex. If you restrict to the tight geodesics in the curve complex, you get exactly that sort of phenomenon that occurs. And if you look at cat-zero square hyperbolic cat-zero square complexes or hyperbolic C'1/64 complexes, and you've got the same phenomenon but with all combinatorial geodesics. So what's the idea? I'm not going to give detailed proofs because, well, sorting out the constants is a bit painful. But at least what's the idea? So the idea is to really understand those quadrangles. You've got your geodesic between x and y, and you've got your element h in the core stabilizer, and you look at the translates of the geodesic, and okay, let's just close that into a say a closed loop. So the strategy to get to that ideal point on the right, so it's in two steps. So the first step is to really understand those thin quadrangles. And by thin, I mean here that the distance between L and between x and y is much greater than the radii of the walls. And two, try to show that those translates overlap a lot. So how do we do that? So since we're in simply connected spaces, we're going to fill those loops by let's call that this diagram. And so what we're going to try to do is to understand the shape of those disk diagrams. And how do you do that? So there's a very useful tool, which is the combinatorial Gauss-Bonnet theorem, which allows you to really understand the shape of those filling disks. And what you want to do after that is use the combinatorial geometry of the space to say that if you have another such quadrangle associated to another element h prime, then it's going to have to the associated disk diagram are going to have to overlap a lot. That's what we want. So how do we do that? I'm just going to get the case of this compensation complex case is much easier. So I'm going to outline the idea. So first we need to understand the shape of those filling diagrams. So we got the following lemma. So it's going to be a lemma without words. Proofs without words, and we get the lemma without words. for every R, there exists an L of R such that. So you've got your filling diagrams. If you're far enough, so a distance LR of the endpoints, then your two geodesics, gamma, the subsegments and the translate, actually bound what's called a ladder. So just to simplify in that talk, I'm just going to assume that the two geodesics are disjoint. So it means that between that portion of the geodesic and the translate, you can actually just put one polygon. So they are overall distance 1 for an appropriate metric. Okay, so in order to do that, we really use the combinatorial Gauss-Bonnet. So actually, there's a recent paper by Cashen, Gruber, and Hume that really classify all those geodesic quadrangles. But just to prove that very particular lemma, I really don't need it's a couple of lines using the Gauss-Bonnet theorem to prove that. Okay, so that's the first step, understanding those triangles or big portions. And now, how do you understand the overlap? So let's assume that there's another one. So you do the same thing. You know that above this is going to look like a ladder, so a sequence of polygons one after the other. So because we are in a C prime 1 over 6 T4, so T4 means that the length of vertices have girth at least 4. Which means that we cannot have something like this. This is not possible because we would have a loop of length 3 in the length. So it's necessarily going to look like this. So the various polygons piling up, like matching perfectly. And now how do you conclude with just like a standard reasoning using a small constellation theory? C prime 1 over 6 means that whenever two polygons intersect, the length of the intersection is less than a sixth of the overall length of the polygon. So here we've got such an intersection between those two, here as well between those two, here as well between those two, assuming that those two polygons are distinct. So the overall length of this would be less than 3/6 or a half. So this portion here would have to be more than a half of the length of the polygon, which contradicts the fact that you are geodesic. So it's really just a standard reasoning using the C prime over 6 condition implies that those letters coincide. It's actually like that. So we are exactly in the case that we wanted. We've got those two disk diagrams which have a very big overlap. Where actually I'm saying big, but I can force it to be as big as I want once I've chosen the distance between x and y to be as big as I want. And once I've done that, then as before, we can sort out and check that everything works the same way. So it's really a strategy that can be applied to various cases. So small constellation complexes, also for K0, hyperbolic K0 square complexes. So here again, you have to understand long portions of quadrangles. In the case of K0, hyperbolic K0 square complexes, it's a bit more complicated. We don't have such a neat picture, but you can show that very large portions are going to isometrically embed in the Euclidean plane, which really helps you to understand the shape of such of long portions of those disk diagrams, and then you have to play a bit with the combinatorics to show that again you're going to be forced to overlap a lot. Okay, so once you have that, those equivalences between asymmetricity and weak asymmetricity, and the same for the WPD condition, so you're generally quite happy, because it's much easier to check now. It's just a question about stabilizers of points. So to give an example, just give an example of a group that I like a lot, a different group. Riemann groups were introduced by Hickman in the 50s. So they're given by generators and relations cyclically. So every generator conjugates the next one to its pair. So they were introduced by Hickman in 51 as the first example of infinite, finitely presented groups with no non-trivial finite quotients, so violently non-visibly finite. And were used to construct the first example. Sorry? Yeah. At least 4, and before that it collapses to the trivial. So these are very interesting groups that have been used to construct examples or counterexamples in group theory, but from a geometric viewpoint they're also very interesting. So you can realize them as polygons of groups, so the high-dimensional generalization of graphs of groups. So you can do it for n equals 6, for example. You can analyze them as polygons of groups with bumps-like solitar VS12 on the vertices.